Great pleasure to have today Andras Vasy from Stanford, you obtained your PhD from MIT in '97, where then a Sloan Fellow, well, during your PhD, you were a Sloan Fellow, followed by being an assistant professor at University of California, Berkeley, assistant professor at MIT, and so on. You became a professor at Stanford in 2005 and are still there, and as far as I understand, and it's a great pleasure to have you today talking about one of your many interests which concern micro-local analysis, n-body scattering, symmetric spaces, wave propagation, inverse problem analysis on manifolds, and many more. Thanks for coming.
Thank you so much for the very kind introduction. It's a great pleasure to be, well, at least virtually in Leipzig to give this talk. So let me start by sharing my screen. Let me just make sure I'm sharing the correct thing. Yes, okay. So I'm very grateful for the invitation from both Stefan Hollands and Johan Tan. What we'll talk about is the Feynman propagator and its positivity properties. And of course, this has a very long history, and I will, and sort of many respects of many things one can talk about. So I will be, of course, just concentrating one particular aspect. And so part of what I'll talk about is joint work in some combination. So this is, I mean, those are a few years ago with Georg Redmann and Haber, as well as Michael Rochna. Okay, so so just the setup, right, is the wave equation on Lorentzian spacetimes, and so we have a symmetric 2 cotensor, and doesn't really matter but which way the 1 and the n-1 is, but I like 1 plus and n-1 minuses, but it's neither here nor there really. So usually one thinks about the Cauchy problem for this. So you have take embedded space like hypersurface and then specify the function you're trying to solve and its normal derivative at this hypersurface. And so locally there's a unique solution, and then if you have global hyperbolicity, then which one way to put it is there's a global time function, then you get a unique global solution. So that's the Cauchy problem. Now you can rephrase it a bit. So I mean, you know, when you have an operator so I'm very far from being a functional analyst, but you know, it's a sort of very nice way to think about things functional analytically. When you have an operator, the first thing you want to do is to invert it. Of course, you need some function spaces and things like that for it. But anyway, so a way of rephrasing the Cauchy problem is to look at the inhomogeneous equation. So you know, box U is equal to F, and then for a Cauchy problem, the two rephrasings are the forward and the backward problem. So if so, let's just say there's a time function t, and the right hand side F is supported in t bigger than t0. And you want to find a u which is supported in the same region, and similar with the analog of the backward. So F is supported in t less than t0, and you want to find a u that's supported in t less than t0. And so one nice thing about this is that this way you don't really have to choose a Cauchy surface. Anyway, these inverses are the forward or retarded and backward or advanced solution operators. And then, I mean, of course, and these are of course very natural from a PDE perspective. So natural question is, you know, what other reasonable inverses of box G there are. And so the claim is that in reasonable settings, so I have to say something about what reasonable setting is, but in some reasonable settings anyway, there are two more natural inverses, the Feynman and the anti-Feynman propagators. Which of course, I mean, there's a reason why I quote Feynman, so they play a role in quantum field theory. So these propagators are somehow much more global in a sense than the advanced and retarded solution operators, right? These advanced and retarded, so forward and backward in time, really come from the local solution theory, local solvability theory for the wave equation. This Feynman, anti-Feynman propagators are somehow much more global. So even the local behavioral solutions depends on the global structure of the space-time. So in terms of local analysis, this dependence is via a smooth solution, so a smooth contribution. So even if you have, say, a singular right-hand side f, the dependence on the global structure as opposed to the local structure is via adding a smooth function to it, to the solution. Okay, so this is not very specific. So I'm trying to say some very general things without having this setup, because somehow the whole philosophy is very general, but then of course it's hard to make a general setup both understandable and self-contained. So anyway, so the settings in which I talk about these inverses are non-trapping, which basically says that the null geodesic flow, so you're looking at Lorentzian metric, you have light-like or null geodesics, and so that should have a good global structure. So of course, locally nothing can happen; it just looks like Minkowski space, but globally it can be quite interesting. And so a concrete example is symbolic of order 0 Lorentzian metric. So the coefficients, right? So you write the matrix, so this is going to be a metric on Rn, and you write it as, so let me just write it up here. So I can write it as Gij, dxi, dxj. And the coefficients, these Gij's, the metric components, are symbols of order 0. So if you differentiate them, you get extra decay. So it's like, this is the typical sort of asymptotically flat situation also in the Riemannian setting. Okay, and then so metrics like this, for which, and again, this Minkowski space really, for the relevant aspect, is really, you're thinking of Rn as a cone over a sphere. Well, Rn minus the origin as a cone over the sphere, a non-metric cone, and it's really, you could change this cross section, that is the sphere also. So it's not really Rn is not really relevant here. Any case, so metrics like this, for which the null geodesic flow has a nice sourcing structure. So this is something that I will explain later on. In the concrete Minkowski or asymptotically Minkowski case, this would be, so again, you're supposed to be thinking about everything in phase space, so in the cotangent space, and the source and sinks will be somehow along the light cone at infinity in phase space. Okay, so again, I will be more concrete in a little while. Now, a nice way. So I just want to give some examples. So it's not. I'm not just talking about Minkowski space. There are various generalizations of this. This is one potential, one direction. Anyway, so a nice way in general, right, to encode inverses, or the obvious thing for a function analyst, which again I am not, but anyway, is the choice of function spaces. Different spaces correspond to different inverses. So you really have to think, when you want to invert an operator, you really have to think, what is its domain and what is its codomain or target space. And at the very least, one would like to have a Fredholm theory. So up to finite rank or finite dimensional obstacles get the invertibility. Okay, and so the spaces on which we work will be based on kind of weighted Sobolev spaces, but these are going to be variable order weighted Sobolev spaces. So the Sobolev space, so I will give you a couple of examples in a moment. So there are two orders, or I mean, it could be more, but so some concrete situations, it's going to be two. I mean, in others, it could just be one. That's going to be actually the main thing I will talk about in most of this talk. So there's some orders. So let's say two. I'm calling S and R. So you should think of S as a differential order and R as a decay order. And again, there are going to be examples in a moment. And one of these orders should be variable. So it's not just a number, but actually is a function on phase space. So that would be your cotangent space of the underlying manifold. And it's supposed to have some properties like monotonicity along the Hamilton flow in phase space, at least along the lifted null geodesics. And then also supposed to satisfy certain additional conditions. So we'll again see this a little bit later, but so the thing I want to emphasize now is that that the function spaces will be some sort of variable order Sobolev spaces or things based on these. And you know, which of these orders is variable depends on the underlying operator that we're thinking about and the corresponding operator algebra. So for example, for the wave operator in the setting I just mentioned, this algebra will be the so-called totally characteristic or B pseudo-differential operators of Marrow's. And it's a decay order that, so the decay order is constant and it's the differential order that's variable. So without saying what these B operators are, let me just say what they are. What is regularity? So if S were a constant, and let's just say R is 0, so there's no weight. What is this space? So what you're doing is you're measuring regularity, at least outside compact sets. So in compact sets, it's just a standard Sobolev space HS. But outside compact sets, you're measuring regularity relative to homogeneous degree 0 vector fields, like xi times ddxj. And so you know, having S of these derivatives would be the constant order version. And so this, by the way, is exactly the things, the vector fields which encode symbolic behavior. So if I just go back for 1 second, let me see if, yeah. So a different way of writing this estimate on this metric coefficient is for each derivative, I put one of the coordinate functions like xi to the left-hand side. So to be like x to the beta d alpha gij is bounded by a constant where beta has the same length as alpha. Okay, same number of same polynomial weights, same number of monomial factors as derivatives. All right, so so that's one example. Now, so a closely related question to all these invertibility and domains, etc., is the behavior of the spectral family. So now it's box minus lambda, and then especially it's a natural thing to start by thinking about what happens when lambda is not real. So it's a complex number, which is not real. And so again, under suitable global assumptions, we get the invertibility of box minus lambda. And then concretely on what kind of spaces, they will be either what corresponds to the Feynman or the anti-Feynman propagator. So the Feynman, the anti-Feynman function spaces, and this depends on the sign of the imaginary part of the spectral parameter. So, and in a concrete sense, so as you let the imaginary part go to 0, so these inverses that we have, an imaginary part is non-zero and has a sign. In the limit when lambda goes to the imaginary part of lambda goes to 0, this will converge to the in appropriate sense to the Feynman or the anti-Feynman inverses. So so from all these inverses that we have when lambda is real, there's one singled out when you make lambda non-real. When the imaginary part is positive, this will be the Feynman. When the imaginary part is negative, this will be the anti-Feynman inverse. And then so those are the only inverses then that are sort of make sense in terms of the overall function spaces. And then when you take a limit, so this is the real line. When you take a limit to the real line, they will actually converge to the real lambda Feynman anti-Feynman inverses. And so in this case, the operator algebra is the most standard operator algebra one can really have on Rn. So I will talk about this a bit later. So and in particular the Sobolev spaces. So it looks slightly funny because so so it's called, sometimes it's called scattering pseudo-differential operators, but it's just the standard pseudo-differential operators that, let me just write out the estimates, right? So the estimates look like this for symbols. So these will come up in a moment. You will have estimates like this, that this thing is bounded by a constant times, let me write it as x to the power, well, it doesn't matter whatever the order is, let's go with L minus alpha times C times M minus beta. So again, I will discuss this in a moment, but the point is that if you differentiate in X, you get extra decay in X. If you differentiate in Xi, you get decay in Xi. This is one of Hormander's algebras, which was earlier already described by Parenti and Shubin. All right. So anyway, so these are the, and then the Sobolev spaces are really the standard weighted Sobolev spaces on Rn. Just take this honest Sobolev space on Rn and then put polynomial weights in front of it. And then in this case, it's the decay order. So not the differential order, but the decay order that's that would need to be variable. Okay, and then so one thing that this in turn relates to is the essential self-adjointness of the wave operator on compact supported C infinity functions, which ends up being a regularity statement for these non-real spectral parameter inverses. So when the spectral parameter is non-real, we get these two. So we get an inverse on different function spaces when the spectral parameter's imaginary part is positive or negative. And you basically want to say is that in fact these inverses map to a subspace of L2. So there's really a comparable domain for box plus minus I on which you have an invertibility theory, as is needed to have a domain for a self-adjoint operator. And then once you have this, then it's not really surprising that the differences of these propagators, so the limit when, so here lambda is real, and I'm taking the limit from either above or below the real axis, that the difference up to a factor of I, so I see I have two different I's in this. There's the two I's should be, these are the same I's. So the positivity is really of this difference is just the positivity of the spectral measure. So in fact, this whole discussion is not really specific for the wave equation. It's really a general non-elliptic phenomenon. So what I will do is, rather than having this like so far, I already had these two different kind of Sobolev spaces. One was this totally characteristic operators, another one like based on vector fields at a homogeneous of degree 0 at infinity in Rn. The other one was this scattering algebra, which is a standard Sobolev space based on the translation vector fields. So really, this has very little, from the fundamental analysis perspective, this has very little to do with this non-compactness of the underlying space, and it's much easier. Like there's much less to say if one talks about compact manifolds without boundaries. So I will discuss the sort of fundamental analysis part mostly in that context, because there's less to say. But everything is completely analogous in general. There's really no more complicated. Okay, but another thing I wanted to say about the second order PDEs, right? So the wave equation is that in fact ultra hyperbolic PDEs. So we have a bunch of plus signs and a bunch of minus signs, and more generally the Laplacian associated with metrics of arbitrary non-Riemannian signature with suitable global conditions is in fact completely analogous. So I don't know, ultra hyperbolic PDEs somehow have a bad reputation, but in fact they're completely like the wave equation except for the Cauchy problem. So there's no analog of the Cauchy problem. And this is related to, as we'll see, to the characteristic set or energy shell having just one connected component, and the only reasonable inverses are the Feynman and the anti-Feynman inverses. So this is not the fault of the operator; it's the fault of wanting to think about the Cauchy problem. So it's a human, not the fault of the operator, but of humans. All right. So now, I should say at least a little bit of something about outlook, that of course, this is related to quantum field theory, and there's been a lot of work on this, including by various aspects of it, including by several members of the very distinguished audience, like Stefan Holland, Johan Zahn, and I think I saw that Jan Derezinski and many others are here, Svederhagen and many others. So anyway, in terms of general outlook of what I'll explain, this is closest to works of Derezinski, Christian Girard, Dietrich Hefner, Simpson, and Rochna. So in fact, I became interested in these sort of problems after talking with Christian Girard, and then like the positivity issues, and in the self-adjointness issues after discussions with Jan Derezinski. And in fact, he had, before I started working on this, he had partial results with Simpson on this. And then more recently, there's I should say, it was also been work on self-adjointness issues by Shu Nakamura and Koichi Taira in a more restricted setting. So maybe just one more comment about QFT, although I'm not really going to be talking about QFT at all. Sorry about this. Is that everyone is definitely interested in positivity properties of various propagator differences, and not really the extreme ones. So somehow the extreme ones and the Feynman and the anti-Feynman, and the positive of their difference, I mean, with the correct order and the correct I put in front, is related to the spectral measure being a positive measure. But one really also is interested in say, the differences between one of the other, like advanced or retarded propagator and the Feynman propagator. And so I will have some more comments about this. But so in this sense, in this setting, right, we have these global inverses, so we have no freedom whatsoever. And the conclusion that one would have is that these other differences one would like to have, I mean, again, with the correct sign and I, are not really positive, but are positive up to a smoothing error. And again, I will comment on this later. So I just wanted to sort of point out that this is not quite doing what one would really like to have from a QFT perspective, but it is giving one Feynman inverses that come from a global inversion, and so one has no choice. I mean, there's no freedom of what one does. Okay, so I will now sort of completely change gear and sort of start from scratch in a sense, discuss microlocal analysis. So maybe any questions at this point? Okay, so if not, I will. So I want to start by talking about the propagation singularities, because this had a major impact both on microlocal analysis and on QFT. So the work of Duistermaat and Hormander in the early 70s, maybe 71, and Radzikovsky in the mid 90s were quite important. And so to set this up, so I'm just going to say a few things quickly about microlocal analysis. If you started and slightly imprecisely, so if you started a manifold, so without boundary but not necessarily compact, for example Rn, then so differential operators are just operators, so acting on some function spaces on the underlying manifold, say complex supported C infinity functions or something like that. They're essentially quantizations of symbols on the cotangent space. So in local coordinates, you can, so local coordinates means in particular that you would, if it's really local, that you want to think of this x variable sitting in some compact set of the underlying, well, on the coordinate chart. And the psi is the dual variable, so the momentum variable, or the fiber of the cotangent bundle variable. So being a symbol, x is compact, so I can't really have a decay statement in x, but if I differentiate psi, I get decaying psi. So you have some overall order m, and relative to that, I get more decay, like polynomials, polynomial psi. And then the quantization is just the usual sort of Fourier transform-based map. So I wrote down the left quantization. You can do various other things. And so the important feature here is what happens as the momentum variable goes to infinity. So one could also do a semi-classical version, but I'm not going to do that right now. So the important thing is what happens as the momentum variable goes to infinity. And so the symbols of order m correspond to growth as this psi to the power m. And then often this is not really needed, but maybe it's a bit more intuitive. Often one considers symbols p, which have an asymptotic expansion in psi as psi goes to infinity, where these pj's, I should have said here, these pj's are then homogeneous of degree 0. So at least asymptotically. So I think we have a statement like that on the next page. Okay. So okay. So the behavior as this momentum variable psi goes to infinity is referred to, well, at least by me and some others, as but of course not by many others, as fiber infinity. This being the fibers of the cotangent bundle, and you know, this infinity is a very loaded word, and you know, one might be tempted to give oneself too much freedom with infinity, as infinity is too far. And so to force oneself to be reasonable, you can either encode this behavior as psi goes to infinity by using, by quotienting by dilations in the fibers, so of the cotangent bundle. So you're really working with the cosphere bundle. Or instead, what's even better is to really compactify the cotangent bundle to a Bohr bundle. So anyway, for purposes of this talk, I think I would just do the usual, much more common quotient. So right, so the cosphere bundle is just looking like this. So this is the underlying manifold, and this is the cosphere bundle, so just spheres over each point. And then to connect the geometry of the cosphere bundle to the analytic objects, if you have a function b, little b on this S star m, then you can consider it as a homogeneous degree 0 function on the cotangent bundle. And of course, you know, there's a silly thing about the 0 section and dilation. So you have to do something like regularize things there, but use a cutoff or something. So modulo smoothing operators, so modulo irrelevant things. You can therefore think about these symbols b. So this function is an S star m as symbols of degree 0 and order 0, and thus giving rise to operators of order 0. And you think of these as microlocalizers. So maybe this is my support of b, and then so it's like a bump function sitting there, and then you think of the corresponding operator capital B as a microlocalizer to this region, and so it sort of kills everything else, annihilates everything outside this this closed set, the support of B, and is non-degenerate, so invertible in a sense, where this function B is strictly positive or non-zero for the matter. And so this this symbol, this function little b, from which capital B came, is the principal symbol of it. And so we have a comment in a moment about the differential operators, and the relations is exactly the same thing. I mean, that's there's a common framework for all pseudo-differential operators, including differential operators. And another name that was, I think, introduced by Hormander for the support of this B, little b, is the wavefront set of the operator capital B. So they're just interchangeable, at least for this kind of B's. Again, I'm not being super careful, but so this is the, I think this gives a more intuitive picture than if I just give a fully analytic statement. And so more generally, right, the principal symbol is just the leading term, so captures the symbol in SM, modulo one order lower symbols SM minus 1. And for differential operators, just taking real the leading terms. All right, so and then ellipticity is just the at the point is just the statement that so at least in this setting where which I'm sort of implicitly using whenever convenient, that you can think about. So here the principal symbol was in general was an element of a quotient space, but often you can take a homogeneous representative, like for differential operators. So I will just, for simplicity, like or like for these little b's, right, which were really just order 0 homogeneous of degree 0 functions, or instead equivalently just functions in the cosphere bundle. Okay, so anyway, so ellipticity is just invertibility once you impose homogeneity. I mean, normally it's phrased in terms of bounds, but it's the reason why it's phrased in bounds is because there's this infinity out there, and who knows what happens. So by using the dilation action or compactifications, you can state much in a more sort of transparent, perhaps, manner. Anyway, so elliptic estimates are so again the operator is elliptic if its principal symbol is invertible, and near elliptic points you have elliptic estimates. So they look like this. So again, the picture I want you to have, all these operators B are going to be zeroth order, so differential operators that arise from functions on the cosphere bundle. And so the picture I want you to have is, here's my cosphere bundle of M. And say I have a B1 that looks like this. So this is the support of B1 really, but you know, it's hard to draw things. Anyway, so here's my B1. And I can, and so it's a positive inside. I can estimate B1U's, which you think of U microlocally on this set in phase space, using PU in a slightly bigger set. So this whole thing would be, do it like this. This would be B3, supported B3. So, so if you have control of PU on this bigger set, slightly bigger set, then you get control of U on the smaller set. And again, this is an nth order operator. You will control U in the sub-Left space HS microlocally, provided you control PU on this slightly bigger set in HS minus M. And again, there's a trivial error, as is usual in this sort of microlocal analysis. So it's a U in basically any weak norm, so whatever weak sub-Left space norm. So that's the usual microlocal version of an elliptic estimate. Right, so a global estimate will look the same. You just skip all these B's and you just do everything global. If you have a global elliptic operator, it's a standard globally elliptic estimate. Okay, but the main interest now is here in non-elliptic operators, and concretely when you have a real principal symbol, then you have which is the case for these wave operators, etc. Then the main result is propagation singularities along the bicharacteristics, so i.e. along integral curves, the Hamilton vector field. So this is basically classical dynamics. So this is inside where the operator itself is not elliptic. So elliptic said that P was invertible or non-zero. So non-elliptic is that P is 0. And so the Hamilton vector field is, right, just a standard Hamilton vector field given by the symplectic structure. And so the theorem is Hormander's theorem, which I will state in a moment in an estimative way, rather than in a maybe more standard wavefront setting way. But before saying it, again, I want to make this more concrete by thinking about the more like getting rid of infinities by thinking of the cosphere bundle. So you know, when you have this Hamilton vector field, it's, you know, some homogeneous. If P was homogeneous degree M, it's homogeneous of degree M minus 1. So, but you can think of this by possibly multiplying it by some elliptic prefactor as inducing a vector field in the cosphere bundle. So if it's homogeneous of degree, if the vector is homogeneous of degree 0, it will act on homogeneous degree 0 functions, which are just functions on S star M. Okay, and so if I do this, so again, let me draw a picture of, again, so this is M, this is S star M. And so my induced vector field, which I would just keep calling HP. So it's some vector field like this. I mean, these are some integral curves. So this, of course, may vanish at some point. And so what that corresponds to is that when I'm in the ambient space, the cotangent space, so without doing this reduction, the vector field is a multiple of what I quotiented out by, so the dilation vector field. So, so the only places where this propagation statement of Hormander is vacuous are these radial points where the HP is a multiple of psi d psi, and these points in the S star M picture are just critical points, stationary points of the Hamilton flow. So maybe you will have I don't know, maybe let me just get rid of this, and maybe you will have something like this. You have a sink, something like that. Okay, so this would be this point here would be a radial point where this Hormander theorem that they will have in a moment doesn't say anything. Okay, so let's see. So the propagation singularity estimate then looks like this. So again, this is an estimative version. So what this says is that you can propagate estimates. So so you want to, again, just like for the elliptic estimates, you want to control U in some region. So say this B1 region. And so what this says, it's a propagation statement. So it's not quite like what was in the elliptic world, that if you know that if you control PU, then you control U, or you certainly have to control PU. But in addition, you also have to control U somewhere else, and then you can propagate this estimate. So you have this, I did this in this parabola-shaped region for various reasons. This sort of works nicer beyond the most trivial settings than what one can get away with in the trivial settings. Anyway, so I have this slightly larger region in terms of width, like in terms of integral curves of HP, B2. And the feature is that whenever I take a point, like say this point, in the support of B1, so that's the closed green region, if I go, in this case, backwards from it, I can make it to the set where this where this B2 is actually strictly non-zero, so say positive. And so the propagation singularities theorem in this estimative version says you can control U in this green region, in the B1 region, if you control it in the red region, plus control PU in again a slightly bigger region, which I didn't really indicate. Again, in its modulo trivial terms. And this is basically, so one proof of this is via positive commutator estimates, which are basically microlocal versions of energy estimates, like the standard energy estimate for wave equations, but done in phase space. Okay, so a complication for this global non-elliptic theory, which will come up, is that, as I already mentioned, you often need variable order Sobolev spaces. So I'm just doing compact manifolds, so there's only one order. And so this already came up in the work of Unterberger and Duistermaat in the early 70s. And so for this, you will take a real valued function on your cosphere bundle. Again, the cotangent bundle has this non-compactness property at phi bar infinity. You somehow want to encode that, so that's hence you work on this quotient. And then basically, you just say that the Sobolev space HS is that you have some background space, which is very weak, HS0, and you just demand that when you have you can just fix a single elliptic operator. So say one with principal symbol norm psi to the S with respect to some Riemannian metric. But again, S was a function, right? So keep in mind that this S is, you can think of it, it's a function of the cosphere bundle. So if you want, locally, you can think of it as something like this. It's homogeneous of degree 0 if you want in another way. Anyway, so you take an operator with symbol like this. It's a slightly weaker class in terms of exactly what happens in differentiating psi, hence this psi delta above. But anyway, let's ignore that. Yep. The question. Anyway, and so you simply say that HS is just a space of U's in, again, some background space such that AU is in L2. So just a version of the, I mean, that would be one way of defining the standard Sobolev spaces if one really wanted to. And then two differential operators of order M will map HS to HS minus M continuously still. And then one thing I want to point out that is estimates, is propagation estimates, and also the elliptic estimates are valid. For the elliptic estimates, there's no condition. For the propagation estimates, the condition is that you need monotonicity of the correct sign along the flow. And so basically in some let me see, so if I'm so it's not exactly clear what I meant by forward and backward here, like which directions, which would basically your estimate should be getting weaker as you you go along the flow. So so S would be in this case, if you want to propagate in this direction, S would be decreasing along the flow. So you say, okay, well, I mean, that's sort of trivial, right? If I can prove a constant S estimate, of course, it's trivial that it's I get an estimate in a weaker space. I make it weaker on B1, but it's not really the case because I didn't quite say anything about PU, right? There's the right-hand side. The PU plays a key role in this estimate, and it's in the space HS minus M plus 1. So it's a loss of one derivative relative to the elliptic estimates, as usual for wave equations. You know, so you're also along the right-hand side to become weaker along this flow. Okay. Back to Duistermaat and Hormander. So they constructed parametrices, so approximate inverses, for operators, at least microlocally, when this Hamilton vector field is non-radial. And basically, they used the Fourier integral operator framework that Hormander constructed to reduce to a model case, which is just the first derivative along a coordinate. And then, in particular, gave a proof of propagation singularities. Well, another thing that they did was to show that if the characteristic set has k connected components, then there are 2 to the k distinguished parametrices. And the distinction is that in each connected component of the characteristic set, you get to decide in which direction you solve away singularities, so forward or backward along the Hamilton flow. You can also phrase this in terms of the wavefront set of the Schwartz kernel of the parametrics. In any case, the point I'm trying to make is that there are this. So already in this work, this distinguished parametrices came up. I mean, there are of course lots of other parametrices you can take, because you can take say linear combinations, convex linear combinations of them, right? If you really just want that, you apply the operator to whatever the output is supposed to be, that's supposed to give you the input. You can add solutions of the homogeneous equation, basically. Anyway, so it already came up in their work, and in particular, this distinguished notion of distinguished parametrices. There are 2 extreme cases. One is that, I mean, in fact, there are 2 rational cases if one is just an outsider and one doesn't think about PDEs. The two really distinguished cases are when in each component of the characteristic set, you propagate the estimate forward along the flow, which if you think about it, like the wavefront set propagates, singularities propagate backwards, or you propagate the estimate backwards in each component. So these are the estimate forward is the Feynman, the estimate backward is the anti-Feynman parametrics. And in fact, answering a question of Whiteman, they also showed that one can choose these distinguished parametrices. Again, these are parametrices, so approximate inverses, so that their difference from the Feynman parametrics is positive. Which is sort of important for this QFT purposes that I already mentioned. And then Radzikovsky used this to explain in the microlocal language the more traditional Hadamard condition in QFT. So for the so going back to the statement. So for the wave operator in a globally hyperbolic connected space-time, you have 2 connected components of the characteristic set, like the light cone that over each point has its 2 halves. And then there are 4 choices up to smoothing: retarded, advanced, Feynman, and anti-Feynman. And so all this is up to smoothing. You are on a non-compact manifold, so there's quite a lot of freedom. I mean, smooth is strong on a compact manifold, smooth relative to distribution. It's very strong on a compact manifold, but it's very weak on a non-compact manifold. There's a big infinity there, who knows what happens. And so they also state they don't see how to fix this indetermination. And so to do this, you actually have to work globally. And so you really need an operator to invert. And so the motto is to think globally and act microlocally. So you want to really do global inversion using microlocal estimates. All right, so I'm just going to quickly recall the general sort of Fredholm setup. So, so the general theorem is that again, I'm not too specific on the non-elliptic settings considered here because it will be a long list and I have to say various things about it. But say think of Minkowski on perturbations of Minkowski that I mentioned earlier. So, so if the characteristic set has k connected components, then there are 2 to the k natural Fredholm problems for p, specified by the direction of propagation in each connected component. And the difference of the extreme generalized, if you don't actually have invertibility, inverses, I mean, you have it up to finite rank, but doesn't mean that you have invertibility, is up to factors of I positive. And so, right, so Fredholm theory is just invertibility up to fine dimensional abstraction. So what you want is that you have an operator between a domain and the codomain as closed range, continuous as closed range. The kernel and the co-kernel are finite dimensional. As I said, these spaces will be essentially weighted Sobolev spaces. I have a comment about the essentially with variable orders typically. The generalized inverses correspond to the Duistermaat Hormander parametrices. But when you have a parametrix, again, you have this indeterminacy, which, because you're in a non-compact situation, is huge. But here there are basically no choices. I mean, you choose which one you want to take, and then if it's not invertible, then you choose something about the generalized inverse. But that's it. Okay, so I just want to record that the Fredholm property is really comes from Fredholm estimate. So you have to estimate, u in terms of pu. P is your operator, modulo some very weak norm of u. So basically the compact inclusion between x and z1, and you need the dual estimate for the adjoint on the dual spaces. So I will be underemphasizing the real non-compact settings. I would say something at the end, but I will be underemphasizing it because it's analytically is exactly the same that's happening, and then I will have to say more. I just want to point out that in the elliptic world, of course, these are just the elliptic estimates, right? They you just take standard Sobolev spaces, and the elliptic estimates applied both to the operator and to the adjoint on by picking appropriate. So I wrote it down with an HR estimate. For the direct estimate, you want to take R equals S. For the adjoint estimate, you want to take R equals minus S plus M. And so that's what gives you the Fredholm theory. And the choice of S is irrelevant. It's elliptic regularity. So for the non-elliptic problems, you have this loss of one derivative. So instead of having pu in hs minus m, it's pu in hs minus m plus 1. And similarly for p star, we have an estimate on sort of the relevant dual spaces. So the S prime on which V is, that space should be a dual of the hs minus m plus 1 in which pu is in the direct estimate. And so what this actually says is that P is Fredholm. If, say, I decided my target space is just hs minus m plus 1, that's very natural. But then I should make my domain, well, okay, I would like to make my domain hs because that's where I get the solvability theory. But then P will not map it to hs minus m plus 1, so I have to add this extra condition. And of course, this is a Hilbert space automatically. But what's important actually is for almost any purpose, that is a really nice space, like C infinity, for example, is going to be dense in it. And that's because, like in general at least, it's because if I said that P is in hs minus m, I wouldn't make a statement because P is continuous like that. So I'm adding one extra condition. And how do you prove a density statement? Well, you regularize. That involves commutators, and commutators improve the order of the operator by 1. So that's hence you have the density statement. So it's not a crazy space. But if I did hs minus m plus 2, it potentially could be a crazy space. Okay, so here we have the propagation singularities, and again the problem is, so in terms of the elliptic estimate, the issue is like the analog of the elliptic estimate, right? For now, which is now non-elliptic. The issue is how do you start this propagation estimate? So the propagation is always like if something is nice somewhere, then it's nice somewhere else. But I mean, how do you get this B2 part? So that's the question, and that's exactly where the global structure of the Hamilton flow, or for wave equations, non-geodesic flow, becomes crucial. So I'm just saying one thing that can do things for you is if you change your operator. So maybe you think of this Q as a tool. So it's you really care about P, but you modify it to cut off some things you don't care about it. So maybe this Q will be some bump function at zero somewhere, non-zero somewhere else, etc. It should be the same order as P. For these kind of operators, you actually still have, even though the principal symbol is now P minus IQ and is no longer real, you still get the propagation statement. The estimate is still true, provided that Q has the principal symbol of Q has a sign. So you can go one way if it's positive, the other way if it's negative. And so this relates to the Feynman propagators. When I talked earlier about that G minus lambda on say Minkowski space, and when imaginary part of lambda is not zero, now you would think that, wow, this is a lower order term, right? It's a 0th order term. The box is second order, but not in terms of decay at infinity. They're exactly the same order in terms of decay, as you could now see if you say Fourier transform this in actual Minkowski space, exactly the same order. And so this lambda plays a role, like when it doesn't have this cutoff bump property, but the propagation estimate is the analog of what I said about Q. Okay, so one could do some things like that, but I'm going to ignore that from now. So a more natural option is you really want to structure this Hamilton flow. So we're in S star M. So this is a bit of S star M. And what you want, so again, it's a quotient of T star M. So maybe the dilation orbits are coming out of the tablet. What you want is that the Hamilton flow should have sort of source sink structure. So you start from a source and you flow to a sink. So I think I have a picture, maybe, okay, so I have to wait the global picture. So let's just talk about the local aspects of this. So, so again, a natural place is radial sets, right? So remember at radial sets is exactly where in the S star M picture you had stationary points of HP, so just as a general indication of the sort of things to think about. So when this HP is actually non-zero, so it's zero as a vector field, the induced vector field in S star M is zero, but the real one in T star M is a multiple of the dilation vector field. It's a non-zero multiple. So in that case, actually, you can see that the biggest dimension this could have is that of the underlying space, and in fact is a conic Lagrangian in this case. So that's sort of typical situation, and there are other generalizations, but sort of just as an orientation. But in this case, in particular, with Lagrangian, it automatically has the Hamilton flow will automatically have a source sink structure. So this Lagrangian or its quotient by dilations will really act as a source sink. And this also arises in scattering theory, where it was studied by Marrows. So in the scattering theory, of course, the interesting part is what happens at infinity. You are usually looking at something like Laplacian plus, I don't know, G plus, say, a potential minus lambda, something like that. And the interesting thing is the behavior at infinity. So there you would think of these Lagrangians would be conic in the base variable. So this is an Rn, and then you can think of T star Rn, and this is Rn cross Rn star, and the conic behavior, this would be in the Rn variable. This is the R plus action. So we'll remove the origin. And of course, some of the researchers I mentioned earlier on, like Dzerzhinsky and Girard, have actually done quite a lot in the scattering setting, in like even n-body situations. All right, and so to sort of finish up what happens, so what will turn out when you have the source sink pictures? Let me just see whether it's like 2 pages down. I have even more. Here's finally a picture. So okay, so So here's the global. So this should should think of this characteristic set here. This is the characteristic set of the operator. So P is equal to 0, sitting inside the cosphere bundle if you want. So this is supposed to be a torus. So I sort of circle across a circle. So I sort of slightly bent it to make it look more like a torus. Anyway, so here I'm just drawing the Hamilton flow inside the characteristic set. So there's one that's one submanifold here, the L2, that's acting as a source, and another one is L1 that's acting as a sink. And concretely, this picture arises, for example, in actual asymptotically Euclidean scattering theory. And there, the source and the sink as a position are exactly the places where the position and the momentum are aligned. So they have in one case, they have positive multiples of each other. So that's where particles end up. And the other case, it's negative multiples of each other. That's where particles start. So it's very down to earth, actually. But going back to the local picture, so it turns out. So let me not comment on what this actual number is, but there's a actual threshold value, which is basically the order of the operator minus 1/2. There's a modification if the operator is not formally self-adjoint. Anyway, and it turns out that if you are working in a space whose Sobolev order is higher than the threshold regularity, then actually you have an estimate like the propagation singularities estimate, but without the if term, the D2U term, right? So the way propagation singularities is, if something is nice here, then it's nice number here, but you can drop the if part. While if the Sobolev space order is below this threshold, then you can propagate estimates into this L. So concretely, this is, again, these are then the estimates. So if the Sobolev space HS, you have an order that's strictly bigger than the threshold value, then you have an estimate. So again, let me just draw a picture. So say maybe you are at a source and you're looking at something like this. So this is a great situation. You get to control. So you say a microlocally. This is your B1. And then you have a slightly bigger B3. Let me not draw it because it gets very crowded. You can control U on B1 in terms of PU on B3. It's like an elliptic estimate, except there's a shift by one order. That's the only difference. Okay, and on the other hand, if the Sobolev regularity is below this threshold, then it looks much like the propagation estimate. But now you think about this. So say let's say do it as a sink just to vary things. The way you can think about it is that you have control. This is where your B2 lives, and so this is B1. You propagate from outside your sink to the sink, and all this works very nicely, the dualization, etc. And then so the upshot is that you get Fredholm theory just by this. You start, say, at the source or the sink, doesn't matter, one way or another, in a space that has better than threshold regularity, propagate on the Hamilton flow, go to the sink, say if you start at the source, and then propagate the estimate there in a space that has lower than threshold regularity. And so all you need is that the Sobolev order should be monotone along the flow, because that's how we had these estimates. And again, less than and bigger than the threshold at the two ends. And the reason, so one might say, okay, why don't you just make the regularity big everywhere? But great regularity is very good always. Well, you also need the adjoint estimate, which has to be on the dual spaces, and high regularity is dual is low regularity. So, you know, and you need that for P star. Also, you have to get started somewhere. So you have to have high regularity somewhere, which for P means you have to have low regularity somewhere. And that's what typically necessitates, you know, that you have for P itself, you have high regularity somewhere, low somewhere else. This is what necessitates the use of variable order spaces. Again, this was the global picture. So for example, e.g., you could have that S high here, and then S is decreasing, and then S low here. I think I'm out of time. Is it okay if I just say a couple of things about examples?
Yeah, I think it's okay.
Okay. So the the simplest thing, I mean, at least microlocally, the simplest thing is just a multiplication operator, which is very simple, like multiply by x1, the first coordinate, an Rm. So then the characteristic set is just the total phase space over x1 equals 0. And the radius set in this case is just the 2 halves, the conormal bundle of x1 equals 0. So in general, the 0 set is connected, you get 2 Fredholm problems. Of course, you have to work globally. I mean, you have to, I'm ignoring that Rn is non-compact, so I think it's a compact manifold. Or you think that this maybe an Rn, but this replace x1 equals 0 by psi squared minus lambda equals 0, where now I'm calling psi as the base variable. This is the Fourier conjugate of the spectral family of the Laplacian. Lambda is positive. This is the sphere of radius square root lambda. And an Rn, the Fourier, an Rn, the Laplacians in this Fourier transform side, Laplacian minus lambda, becomes a multiplication operator. That's exactly, microlocally has the same structure. And so again, the Fredholm theory in this setting gives exactly rise to the this is a perfectly nice self-adjoint operator. It's very nice and easy in this setting because the only way it's not bounded is in the differential order sense, and it's a perfectly nice elliptic operator. So it's very easy to see that it's that you have self-adjointness. You get the limiting absorption principle resolvent, the limiting from above or below the real axis, and this is exactly what so the difference the positivity of the difference of these is exactly the positivity of the spectral measure. So that's one example of what I talked about. You can make this more interesting if you have so again in this case you had only so one choice with corresponding to 2 inverses forward or backward on the characteristic set because it's one connected component. Now, if you have an asymptotic Euclidean space with 2 ends, say an Rn, another Rn, and glue, that means some compact set. So the operator is perfectly nice and elliptic with Laplacian, and then take Laplacian minus lambda. Now, there are 2 ends, so there's a characteristic set for this problem at infinity because you already saw by the Fourier transform picture. And then now there are 2 components corresponding to the 2 ends. And in each end, I can decide which direction I want to propagate my estimate. So now, of course, I can do the reasonable things, go always forward, always backwards. Those give you the exactly the usual limiting absorption principle resolvents. Or you can try to go the opposite way on the 2 sides, forward on one side, backward on the other side. Why not? So you don't necessarily get invertibility, but you get the Fredholm statement. It's a very unnatural Fredholm problem, one might say. But this is correlated then to the Klein-Gordon equation. Again, say on asymptotic Minkowski space, where the characteristic set now has 2 connected components, and it again has this source sink picture corresponding to the source and sinks at infinity, and again it fits into the scattering algebra. So okay, maybe I should say one more thing. So so you again have now 2 choices with 4 different propagators, and you get the Feynman, the anti-Feynman, as well as the 2 components that correspond to the Cauchy problem, which you could argue that they are a bit more natural than these 2 funny problems for this 2-ended Euclidean space, but in terms of microlocal analysis are exactly the same in terms of structure. And I don't really want to take up more of your time, but let me just end by saying that in if you really want to just look at the actual wave operator on Minkowski-like spaces, and so this is the work with Garedman and Haber, and also with Rochna. Then this analytic setup will be in this 2-differential operator of Marrow's, and maybe I'm not going to give more details on this because I'm already over time. I just want to draw a picture of Rn, or really Rn plus 1, I guess I'm quoting it here. That's so relevant. So you think of Rn plus 1 as well, it's of course a vector space, so it has dilations on it, and so the you can compactify it by so basically the dilation orbit, so compactifying each dilation orbit, adding an ideal point at infinity. So it's at the sphere at infinity. And so this will be the space on which this global geometry would happen. And then the null geodesics or null by characteristics, right? So they are just straight lines in the actual Minkowski space. Then we just connect the antipodal points, which in this compactification looks something like this. So these are the null geodesics. An antipodal point at the light cone, and then and so here's a limiting one, and actually the boundary of this compactification, and then your the order function is what would be monotone. Of course, I drew them in one direction. They also go backwards in phase space, and that would be monotone along this flow, and have some bigger than or less than the threshold value at the sort of incoming and outgoing side, the source or the sink side of this in phase space picture. So sorry for being a bit quick here. Thank you very much for your attention.
Yeah, thank you for your talk. Are there any questions?
May I ask a question? Jan Dereziński.
Hello, Jan. Yes.
Hello. So thank you for a very nice talk. So you mentioned a non-trapping condition. Now suppose you have the simplest situation, so that this means the Klein-Gordon operator on a globally hyperbolic space-time. Is this non-trapping condition automatically satisfied?
Yeah, I wasn't very specific of what this non-trapping condition is. So I would say no, because you need more analytic structure for it. So at least, let me put it this way. Certainly in frameworks I have thought about, it's not automatically satisfied.
Yeah, so what can go wrong?
So the okay, so because I wasn't so specific of exactly what structure you want, this is slightly harder to answer. But okay, so the way I was phrasing it in this radio point part is that ideally what I would like is sort of a source sink structure of the Hamilton flow, and certainly this could be much more complicated. So, for example, if you think about like maybe one relatively easy example where this comes up is, say, black hole spacetimes. You have like things like the photon sphere, which acts as some sort of a trapped set. So it has sort of good properties, so you can do things about it, but it's not completely. I mean, there is something to do. So in a weak sense, it's quite possible that what you're saying is automatic, but it's at least for the analysis I was thinking about is too weak.
Yeah, but can you explain a possible scenario for a trapping? I mean, a globally hyperbolic space-time seems to be so well behaved that I mean, how can this geodesic flow be trapped on there?
So the it depends on it depends on the meaning of trap. So I really want to have a very strong version of non-trapping, which is why it can go wrong. So for example, right, so if you have a space-time that say looks like so this is the future of say t equals 0 or something like that, and you have some so in some ways you're happy with null geodesics that cross, these are your horizons, and you're happy with these sort of null geodesics. But you have some other factors, and so you will actually have some null geodesic that doesn't go at this 45-degree angle, but goes straight up to the top. Now, in some sense, of course, this is non-trapping. Your null geodesic is escaping to a space-time infinity, but this is not necessarily so well structured from the perspective of the underlying analytic argument. So right, so in terms of a smooth structure of this space-time, I would have something like this. So I have my two horizons. So I don't know, this is my horizon B, and this is my horizon C. And here I have, again, the same horizon B, horizon C. And so I would have some null geodesics that go happily to some point in the middle. And then the actual null geodesic is just limiting there. So it never actually escapes to these horizons. Okay, so on the other hand, so here's some trap set. And from this trap set, there are some other like limiting null geodesics that sort of escape from there to the horizon, but you sometimes have to go through this trap set. And so there are analytic issues here. So this is something that I do not want to allow, at least for getting a simple result like what I stated.
Yeah, but well, okay. So suppose that space-time is asymptotically Minkowskian.
Yeah.
So this is even both globally hyperbolic and asymptotically Minkowskian, to be on the safe side.
Yeah. Okay.
Then do you need an extra non-trapping condition, or is it automatic?
That's a good question. I haven't thought about this directly. I haven't thought about this recently, so I forget what I thought about it before. But certainly near infinity, it's automatic. Actually, it should be it should be. Yeah, I think it's automatic in this case, because everything that's uniform near infinity is automatically well behaved because the asymptotic Minkowski nature, and from your global hyperbolic saves you on compact set. So yes, it's fine.
Thank you.
Any other questions to Andras? Maybe if not, I had one myself, or I had two perhaps. So one concerns, so take the example of a Cauchy horizon, which is a situation that, of course, you have studied. What can one say about wavefront sets of the, let's say, Feynman propagator near the Cauchy horizon? I mean, I know you have estimates on various weighted Sobolev spaces of, let's say, a forward solution.
Yes.
No, but I mean, really, as a bi-distribution, as a distribution in two space-time points. What can one say? Because I think this would be very important to understand.
So I unfortunately I don't know. The answer is I don't know. But this is something that I definitely have thought a little bit about and want to think much more about. But this is something for which I don't have a clear picture how it sort of relates to what I talked about. So I mean, in particular, even in, say, so one thing that doesn't have Feynman propagators but has the forward and backward solutions that I worked on is like Kurt de Sitter stability say. That's where the sort of horizon pictures come from. So so there the setup was always to actually, I mean, which is sort of needed for stability anyway, but that was not the only reason, because when you perturb your space-time, horizons can move. But that was not the only reason. There's analytic reasons that you always sort of went beyond the horizon. So you get actually finally space-like hypersurfaces, which are sort of acting as Cauchy final or for the forward problem, Cauchy hypersurfaces. And so this is one thing that I have wanted to sort out, but I have not. And certainly, like Jan Dzerzhinsky, for example, and Christian Girard and Michael Rochna worked on some of these null hypersurface versions, but certainly I have not sorted out from this sort of Fredholm theory perspective how microlocally how one should think about the Feynman inverses in this case.
So I'd be interested in really analytic estimates of some Sobolev wavefront.
Right, exactly.
Near the Cauchy horizon, on the Feynman propagator, whichever way you construct it, really. But I think your method seems very well adapted to obtain such estimate. I mean, it looks to me as a non-expert. Another related question. I mean, there's an in renormalization theory. There's a very old trick by Zimmermann where you replace the Feynman propagator, which in momentum space, as you of course know, is 1 on p squared plus or minus I epsilon, where you replace it with where you replace p squared, which is the Lorentzian p squared, by the Lorentzian p squared plus a small imaginary times the Euclidean p squared, which is like your operator q. And so you want to let this small prefactor of q, which in your case it was iq. Now you want it's sort of I epsilon q, and you want to know how this kind of thing behaves when epsilon goes to 0. Is your method? Do your methods give information on this?
Right, exactly. So these are uniform estimates for exactly that kind of operator, indeed.
That's interesting. And can you so this operator p plus I epsilon q? Do you have like a functional calculus? Could you define like an analog of the heat kernel for this? I mean, this would be related.
So certainly not from the. I mean, I don't have a functional calculus for this, but I were to think about how to answer your question. I think that there's definitely promising things in this direction.
Because this is an old trick where where you use if you want to renormalize Feynman graphs, you go to this quasi, you go to it looks very silly at first, but it actually works to go to the Minkowskian world from the Lorentzian from the Euclidean world. But such kind of estimates would be needed. Okay. Well, any other questions to Andras? Also from our students, of course.
I have maybe a naive question. I'm not really into this subject, but I was interested. Is it interesting to solve nonlinear equations with this propagator, or even in flat space? I don't even care about non-flat.
Right. So okay, so of course it's always a question for whom, right? But one thing that's one place where you have these propagators is in the elliptic world, but on asymptotic Euclidean world, right? So the resolvent is automatically like this. The limiting absorption principle resolvent is automatically like this Feynman propagator, and so in fact, Jesse Garelman, who I mentioned, as well as Andrew Hassel at ANU in Australia, and a couple other people, a couple other postdocs in collaborating with them. They are working on Schrodinger and wave equations using. So they already worked on the scattering theory version. So you want to have now nonlinear solutions of a nonlinear equation, which like a nonlinear scattering theory, right? You're specifying an incoming behavior, and then you want to produce a solution which would have some whatever outgoing behavior. So they already have a paper on that, and now they are working on extending this to the Schrodinger and wave equation pictures.
So you mean that this Feynman, I have hard time to think intuitively about the Feynman propagator. So you mean that it's really this specification of asymptotic boundary conditions?
Yeah. I mean, so one way of thinking about it is that you have so in terms of so I would say putting it as the inverse of something, but instead you can think about it as constructing solutions of the homogeneous equation. And so for that, then what you would do is you specify data at your source or sink or wherever, and say you have some unperturbed problem, like a linear equation, like a Euclidean Laplacian, something like that, that you know what solutions look like with the specified data. So now you have a solution for this unperturbed problem, but now you really want to solve some nonlinear equation with that sort of incoming behavior. So now there's an error because you don't solve anymore the equation you really want to solve. You want to solve away your error using, so say in the linear setting, but you perturb now, you're really just using the inverse that propagates estimates away from where you specified your data. So the Feynman propagator really is, so in this Minkowski setting, then what it's doing is that you can think about it, what it's doing is that it's giving you solutions where you specify data at the sources. So for the forward in time null geodesics in the past and the backward in time ones in the future, and then one solution of the wave equation with that kind of behavior at the sources.
Okay, thanks. And
maybe another place where this occurs in physics is if you calculate the S matrix, the scattering matrix in quantum field theory for in and outgoing particles, and then there is a standard perturbative expansion, and this expansion is a kind of expansion where certain graphs appear whose edges are precisely the Feynman propagators, so in physics it's very natural to have the Feynman propagator instead of the advanced and retarded ones in quantum field theory. And so if you wanted to make sense of such Feynman diagrams, one would, on a manifold, one has to know the microlocal properties of these to renormalize these diagrams. So it's a quite a natural object.
Yeah, thanks. Now it's clear.
Any other questions?
Hi, I have a question. So is this a non-trapping assumption, the global setup you have set up, it is sufficient for the positivity of propagator differences? Or do you need something more to ensure the positivity property?
Yeah, so the, okay, so one, as Jan pointed out, I wasn't quite specific enough for what exactly the non-trapping assumption is, but so I really want it in some stronger sense. But so if you have it like that, then the only extra thing that you need, so in principle, what you don't know is you will get the Fredholm theory, but it doesn't give you invertibility automatically. So there are these fine dimensional obstacles in general to invertibility. And so if these don't exist, so basically a trivial null space, trivial kernel and co-kernel statement, then the positivity actually, so you do have the inverses, then the positivity is automatic. If you don't assume away this the kernel and co-kernel, then in an appropriate sense you still have, like in a generalized inverse sense, you still have the positivity. So the positivity somehow comes out from the nature of these sort of positive commutator estimates that give rise to, for example, the Fredholm theory. So it is almost automatic in a sense up to these finite dimensional issues. And these finite dimensional issues, when you actually have a wave equation, so in general, it's harder to say what happens, but when you have a wave equation, then you can use knowledge of the standard propagators for the wave equation to rule out such a kernel and co-kernel. So so these fine dimensional issues. So I mean, very concretely, the sort of things that you get in this say Minkowski kind of settings is that if you have an element of the null space on the relevant Sobolev spaces, then it's, say, for the Feynman, you're trying to construct the Feynman inverse, the Feynman spaces, then actually it's automatically in also in the space that corresponds to any of the other propagators. And so you can think about it as an element of the null space of the wave equation for the standard forward in time problem. And then which now, however, has sort of decay in the say in the past, actually both in the past and the future, and so hence it cannot exist. But in general, when you don't have something like this global hyperbolic spacetime or something like that, then it's not. I don't think it's automatic that you can rule out the finite dimensional issues.
I see. Okay, thank you.
There don't seem to be further questions, at least no urgent ones. So Andras, thank you very much again for telling us about the Feynman propagators. And see you all again. When? That's the question, Jochen. When is the next seminar?
Probably in September.
Well, in September. Then let's hope the pandemic has not raised its gruesome head again, and have a pleasant summer. Bye.
Thank you very much.
Thanks a lot.
Bye.
Bye. Thanks for the.
Bye.